The shaft that twisted while standing still. A Steam Stories documentary script. Runtime 25 minutes. Chapter 1, Cold Open. The main drive shaft stretched 140 feet through the dimness of mill number 3. At 2 in the morning, Frank Holloway walked his rounds with a lantern held low, its flame steady in the still air. The shaft, 16 inches of forged steel, hung motionless in its pillar bearings, suspended above the silent floor like a sleeping spine. No belts ran. No pulleys turned. The entire hall rested in that peculiar silence that only comes when massive machinery stops breathing. Holloway had walked this route 6 nights a week for 11 years. He knew the temperature of every bearing by touch, the smell of every gearbox, the way shadows fell across the machinist's bench at the far wall. But on the night of October 14th, 1891, something made him stop mid-stride. The chalk marks were wrong. Every morning before shutdown, the day engineer marked the shaft coupling with 2 bright lines, one on the collar, one on the hub, to verify alignment when startup came. They should have matched perfectly. They always had. But now, in the lantern light, Holloway could see the lines had separated, not dramatically, perhaps a quarter inch, but unmistakably offset, as if one had slid past the other while the shaft remained locked in place. He stood very still, listening. The hum he'd been hearing, had it always been there? Low and persistent, felt more than heard, like the resonance inside a bell after the clapper stills. He touched the nearest bearing housing. Warm, not hot, but warmer than the October air deserved. The shaft itself gave back a faint vibration under his palm, something rhythmic and impossibly slow. Holloway walked the length of the shaft, checking each coupling, each set of marks. At the second bearing, offset. At the 4th, offset. At the 7th, offset. Always in the same rotational direction, always roughly the same amount. As if the entire shaft had twisted a fraction of a degree while standing completely still. He wrote the observation in the night log with careful script, underlined it twice, and continued his rounds with a growing unease that had no name yet. By morning, the marks had shifted further. The day crew arrived to find Holloway's log entry and a shaft that no one could explain. Thomas Brennan, the chief engineer, stood with hands on hips, staring at the chalk marks as if they'd personally insulted him. Around him, millwrights and machinists gathered in that quiet way men do when confronted with something that shouldn't be possible. "Did it turn?" someone asked. "Couplings locked," Brennan said. "Keyways seated. If it turned, everything turns." But nothing had turned. The shaft's relationship to the building remained fixed. The marks on the pillar bearings proved that. What had moved was the shaft relative to itself, twisting along its length like a wrung towel, except this towel weighed 11 tons and was supposedly rigid steel. Brennan ran his hand along the surface, feeling for heat patterns, for any sign of slippage in the couplings. The metal was uniform, cool now in the morning air, perfectly smooth. "Check every bearing," he said quietly. "I want temperatures, clearances, and oil condition, and I want new marks on every coupling before we run tonight." The inspection took most of the morning. Every bearing showed normal wear. Every coupling seated true. The alignment down the shaft's length measured perfect within a 32nd of an inch, extraordinary precision for a shaft that age, installed in 1884 when the mill expanded. By noon, 18 fresh chalk marks adorned the couplings, bright white against dark steel, witnessed and recorded by 3 separate men. The mill ran its standard day shift. The shaft turned at 72 revolutions per minute, driving 4 floors of textile machinery through an elaborate system of belt drives and countershafts. It performed flawlessly. No vibration, no unusual heating. At 6 o'clock, they shut down for the night, and Brennan himself verified that every chalk mark remained perfectly aligned. "I'll stay tonight," he told Holloway. "We'll watch it together." They made coffee on the small stove in the engineer's office and settled in to wait. Outside, the October evening cooled rapidly, as it had been doing all week, warm days dropping to frost by midnight. Through the office window, they could see the length of the shaft disappearing into darkness, lit only by the inspection lamps they'd left burning at each bearing station. At 11:30, Brennan noticed the sound first. That same low hum, rising from nowhere, vibrating through the floorboards. By midnight, the first marks had begun to drift. Over the next 6 nights, the phenomenon established a pattern. Between 10 p.m. and 4 a.m., while the shaft remained absolutely stationary, it would twist. The rotation was always in the same direction, counterclockwise when viewed from the drive end, and always accumulated to roughly 3/4 of a degree by morning. Then, mysteriously, over the course of the day's operation, the twist would gradually disappear, the chalk marks creeping back toward alignment as if the shaft were slowly unwinding itself. But it was the sound that began to unsettle the night crew. What had started as a barely perceptible hum grew into something more complex, a layered vibration that seemed to have multiple frequencies woven together. Some men described it as musical, others as deeply wrong, like hearing a structure groan before it fails. It wasn't loud. You could hold a normal conversation over it, but once you noticed it, you couldn't stop hearing it. Brennan began taking measurements. The bearing temperatures showed a curious pattern. The support nearest the drive end ran 8 degrees warmer than the others during the night, while the bearing at the far end stayed coolest. During daytime operation, the pattern reversed. He documented shaft diameter at multiple points, looking for expansion or contraction. The numbers stayed constant. He checked the building's foundation, suspecting settlement. Nothing. On the 5th night, a new development. One of the pillar bearing caps, a cast iron piece weighing perhaps 40 pounds, spontaneously loosened. Not catastrophically. No one heard it happen. But the morning inspection found 2 of its 4 bolts backed out nearly a quarter turn, threads clean, as if unscrewed by an invisible hand. "It's building up to something," Holloway said, and though Brennan wanted to dismiss this as superstition, he couldn't quite manage it. The shaft was storing energy somehow, winding itself tighter night after night despite being mechanically locked. The mathematics of it escaped him, but the physical evidence was undeniable. Something inside 11 tons of forged steel was happening very slowly, and it wanted out. By the 8th night, the twist had increased to nearly a full degree. The hum had developed harmonic overtones, and several workers reported feeling it through their boot soles when standing near the bearings. Production continued normally during the day, but the night shift walked the machine hall with increasing nervousness, waiting for the shaft to do whatever it was building toward. The mill's superintendent, James Wickham, convened a meeting in the main office on the morning of October 22nd. Present were Brennan, 2 millwrights, the company's consulting engineer from Boston, and a representative from the shaft's original manufacturer. On the desk between them lay Brennan's meticulous logs, temperature readings, measurements, sketches of the chalk mark positions at hourly intervals. "Warping," said the consulting engineer, a precise man named Aldrich. "Thermal expansion along the length, uneven cooling at night. The shaft bows appears to twist." Brennan shook his head. "Diameters don't change. If it were expanding, we'd measure it." "Casting flaw, then. Internal stress from the original pour, finally expressing itself." The manufacturer's representative bristled. That shaft was forged, not cast. Hammer forged from a single heat, grain structure aligned. We've had shafts from that run operating for 15 years with no issues. "Then the bearings," someone suggested. "Uneven friction, allowing microscopic rotation that accumulates." They tested this. That afternoon, they locked the shaft at both ends with heavy timber bracing, wedged so tightly that 3 men couldn't budge it. They marked it again. That night, it twisted anyway, the chalk lines sliding past each other while the timber bracing remained solid and unmoved. Whatever was happening occurred within the shaft itself, not at its supports. Sabotage came up, spoken carefully. Someone deliberately heating one end, perhaps, or somehow applying torque when no one watched. But the mill ran a continuous guard schedule, and the shaft remained visible from multiple angles throughout the night. Besides, the amount of heat or force required would be enormous, obvious, impossible to hide. "What if," Holloway offered quietly, "what if it's been twisted all along, since it was installed, I mean, and now it's trying to untwist?" The room went silent. It was the first theory that explained the directionality, the nightly accumulation, the way the twist diminished during operation. But it raised more questions than it answered. How could a shaft twist during installation? Why would it wait 7 years to show symptoms? And why only at night, when the mill stood idle? Aldrich tapped his pencil against the logs. We need to measure torsion directly, not just the surface marks, internal stress. How? Wickham asked. I'll need to make some inquiries, Aldrich said. There's work being done at MIT on material stress, new measurement techniques. Give me 2 days. They gave him 3, while the shaft continued its nightly ritual, twisting and untwisting like something breathing in its sleep. Aldrich returned with a borrowed strain gauge, a delicate instrument of his own modification, designed to measure minute deformations in metal under load. It worked on the principle that stressed metal changes its electrical resistance, though only slightly. The device was experimental, finicky, and Aldrich himself admitted he wasn't entirely certain it would function properly on a shaft of this size. They mounted it on the shaft's surface at the midpoint bearing, attaching thin wires that ran to a galvanometer in the engineer's office. The setup took most of a day. By evening, they had a functioning, if crude, measurement system that would show them whether the shaft's internal stress changed over time. What they discovered, that night changed everything. The stress wasn't constant. It wasn't gradually increasing. It was oscillating. Beginning around 10 p.m., as the ambient temperature dropped, the strain gauge began registering regular pulses of torsional stress, not a steady twist, but a wave pattern, building and releasing over a period of roughly 40 minutes per cycle. Each pulse would load the shaft slightly, store elastic energy in its structure, then partially release, but not completely. Each cycle left a tiny residual twist, and these accumulated over the course of the night into the visible offset they'd been tracking. It's resonating, Aldrich said, watching the galvanometer needle swing. Something's driving it at a natural frequency. They tracked the temperature gradient along the shaft. As the evening air cooled, the drive end, nearest the boiler room, stayed warmer than the far end near the external wall. This created a differential thermal contraction. The cool end wanted to shrink slightly more than the warm end. But because the shaft was mechanically constrained at both ends, this contraction couldn't express itself as linear shortening. Instead, it stored itself as torsional strain. But that alone wouldn't cause oscillation. The key, Aldrich realized, was the building itself. Mill number 3 had been extended in 1884, the same year the shaft was installed. The new section connected to the old through a shared bearing wall, a massive structure of brick and timber that carried loads from both buildings. During the day, this wall vibrated continuously from the mill's operation, damping out any resonances. But at night, in perfect silence, the wall had its own natural frequencies. And one of those frequencies matched the torsional natural frequency of the shaft, almost exactly. The wall breathes, Brennan said slowly, understanding dawning. Temperature changes, timber expands and contracts, just barely, and it shakes the shaft at exactly the wrong frequency. Exactly the right frequency, Aldrich corrected. For the shaft. It's like ringing a bell. If you tap it at its natural pitch, even tiny taps build into large vibrations. The building is tapping this shaft 40 times an hour every night, and the shaft is storing each tap as torsional strain. They verified it over the next 2 nights. The oscillations began when the temperature gradient reached a critical point, always around 10 p.m. They peaked between midnight and 2 a.m. when the differential was greatest, and they damped out naturally as dawn approached and the temperature equalized. During the day, the mill's operation swamped the resonance entirely, and the shaft gradually released its stored twist through normal rotation and bearing friction. The shaft wasn't breaking, it was ringing. Aldrich brought in 2 colleagues from Boston, men who'd studied under James Thompson and understood the emerging mathematics of vibration and elastic materials. Together, they spent a week transforming mill number 3 into a laboratory. They installed temperature sensors every 20 feet along the shaft. They measured the building's vibration spectrum using sand-covered plates that revealed standing wave patterns. They calculated the shaft's torsional stiffness based on its material properties and geometry. The numbers told a remarkable story. Shaft's torsional natural frequency, the rate at which it preferred to oscillate if given a twist and released, was approximately 1.4 cycles per minute. This was determined by its length, diameter, material modulus, and end constraints. The bearing wall's thermal breathing, driven by the October temperature swings, occurred at approximately 1.5 cycles per minute, close enough that energy could transfer between them, especially given the long duration of each night's cooling period. But what made the phenomenon particularly dramatic was the shaft's length. At 140 feet, it was long enough that torsional waves, twists propagating along its length at the speed of sound in steel, could reflect back and forth multiple times per cycle. These reflections created standing wave patterns, nodes and antinodes of torsional stress that reinforced themselves over many cycles. Think of it as a spring, one of Aldrich's colleagues explained to the assembled mill workers, but a spring that twists instead of compresses. When you twist one end, the twist travels down the length as a wave. When it hits the far end, it reflects back. If you time your next twist just right, you add to the wave that's already there. Do this for hours, and you build up enormous stored energy. But why doesn't it break? Someone asked. Because steel is elastic at these stress levels. It can store tremendous energy without yielding. A shaft this size can twist several degrees before approaching its elastic limit, though I wouldn't recommend finding out exactly where that limit is. They calculated that the shaft was currently storing approximately 4,000 foot-pounds of torsional energy on the worst nights, equivalent to the energy in a half-pound weight dropped from a mile up, all wound into the molecular structure of the steel itself, held there by nothing but the shaft's own stiffness and the friction of its bearings. The question became, what would happen if it released suddenly? Aldrich ran simulations using graphical methods, plotting stress distributions on long sheets of paper, calculating wave reflections by hand. In the worst case, if all the bearings released simultaneously, the shaft would oscillate violently for several seconds, spinning perhaps a quarter turn in each direction before damping out. The bearings would likely survive. The couplings might not, and anything standing nearby would want to be elsewhere. We need to detune it, Aldrich said finally. Break the resonance. Change either the shaft's frequency or the building's frequency so they no longer match. How? Wickham asked. Several options. We could add mass to the shaft, flywheels at intervals to change its moment of inertia. We could stiffen the bearing wall with steel bracing. We could change the bearing friction characteristics to add damping. Or we could simply insulate the drive end thermally, eliminate the temperature gradient that's providing the initial torsional load. They chose a combination. Over the next 3 days, they wrapped the drive end bearing housings in thick felt insulation, reducing heat transfer from the adjacent boiler room. They added viscous damping to 2 of the midspan bearings by adjusting the oil properties, thicker oil that would dissipate energy rather than allow free oscillation. And they installed a simple friction brake on the shaft itself, a hinged wooden block that could be lowered onto the shaft's surface at night, providing just enough resistance to prevent the buildup of torsional waves. On the night of November 2nd, they implemented all 3 measures and watched. The temperature gradient still developed, but more slowly. The bearing wall still breathed its slow rhythm, but the shaft remained quiet. The strain gauge showed minor stress fluctuations, but they never built into the resonant pattern that had dominated the previous weeks. By morning, the chalk marks had drifted perhaps 1/16 of an inch, trivial, well within normal thermal expansion tolerances. "It's done," Brennan said quietly. The shaft ran without incident for the next 32 years, until the mill closed in 1923. But the engineers who'd solved the mystery of the twisting shaft carried the knowledge with them, and the principles they documented: torsional wave propagation, structural resonance, thermal loading of long shafts, became standard considerations in mill design throughout New England. The phenomenon that plagued Mill Number 3 in October of 1891 was a perfect storm of mechanical circumstances, each ordinary on its own, but devastating in combination. First, residual torsional stress. When the shaft was installed in 1884, it had been manhandled into position by dozens of workers using rope falls and lever bars, lifted bearing by bearing down the length of the hall. During this process, it was inevitably twisted slightly, microscopic amounts at each bearing, but accumulating along its 140-foot length. Once bolted into position, this twist became locked into the structure, creating what engineers call residual stress. The steel remembered being twisted and wanted to return to its original state. But residual stress alone wouldn't cause the observed behavior. Thousands of shafts were installed under similar conditions with no issues. What made this case unique was the thermal gradient. Every evening, as the October air cooled, the shaft developed a temperature difference between its warm end near the boiler room and its cool end near the external wall, a difference of perhaps 15 degrees Fahrenheit along its length. Steel contracts as it cools, about 6/millionths of an inch per degree. Over 140 feet, with a 15-degree gradient, the cool end wanted to be roughly a 1/16th of an inch shorter than the warm end. But the shaft was constrained at both ends, unable to shorten. This constraint converted the thermal contraction into torsional stress, a twist, not a large twist, but enough to matter. Now came the critical factor, torsional wave propagation. When you twist one end of a long shaft, the twist doesn't appear instantly along its entire length. Instead, it propagates as a wave, traveling at the speed of sound in steel, about 16,000 feet per second. For a shaft 140 feet long, this means a torsional wave takes about 8/1000ths of a second to travel end to end. When it reaches the far end, it reflects back, just like a sound wave echoing off a wall. These traveling waves, bouncing back and forth, create standing wave patterns, locations along the shaft where the stress is always high, and locations where it's always low. If you excite the shaft at exactly its natural frequency, these standing waves build up, cycle after cycle, storing more and more energy in the elastic deformation of the steel. And that's where the building came in. The bearing wall between the old and new sections of Mill Number 3 had its own natural frequency of vibration, driven by thermal expansion and contraction of its timber members. This frequency happened to be almost identical to the shaft's torsional natural frequency. Not exactly identical, that would have been catastrophic, but close enough that over the course of hours, energy could transfer from the wall's motion into the shaft's torsional oscillations. Each tiny vibration of the wall would give the shaft a small twist. The twist would propagate as a wave, reflect, interfere with the next incoming wave, and gradually build up a standing pattern. The bearing friction provided some damping, but not enough to prevent the buildup, especially given the many hours of excitation each night. The asymmetry in bearing friction also played a role. The drive end bearing, running warmer due to its proximity to the boiler room, had slightly lower viscosity oil and thus slightly lower friction. This meant that end of the shaft was freer to oscillate, while the cool end was more constrained. This asymmetry biased the twist in one direction, always counterclockwise from the drive end, rather than allowing it to oscillate symmetrically. Finally, the elastic strain energy storage capacity of the shaft itself made the phenomenon visible. Steel can store enormous amounts of energy without permanent deformation. A 16-inch diameter shaft, twisted 1 degree over 140 feet, contains several thousand foot-pounds of potential energy. This energy manifested as the slow, inexorable drift of the chalk marks, the warming of certain bearings, the low-frequency vibration that workers felt through the floor. During daytime operation, all of this was swamped by the shaft's rotation. The bearings' dynamic friction during rotation provided much more damping than their static friction at rest. The temperature gradient reversed or disappeared as the building heated from machinery operation. And most importantly, the building's structure vibrated chaotically from all the running machinery, preventing any resonant coupling with the shaft. It was only at night, in perfect stillness with a specific temperature gradient, that all the factors aligned: residual stress, thermal loading, resonant excitation, wave reinforcement, and asymmetric damping. Together, they created a shaft that twisted while standing still. The solution didn't require eliminating any single factor completely. Breaking the resonance by adding damping, reducing the thermal gradient, and providing a small amount of additional friction was sufficient. The shaft could still develop minor torsional stress from temperature differences, but without the resonant buildup, it never reached concerning levels. What Frank Holloway witnessed that October night was not a malfunction, but rather a demonstration of principles that wouldn't be fully understood for another generation. Torsional dynamics, structural resonance, thermal stress analysis. These would become standard tools in mechanical engineering. But in 1891, they were mysteries, solved by careful observation, meticulous measurement, and the kind of patient reasoning that builds understanding from evidence rather than assumption. The shaft that twisted while standing still became a teaching case, documented in engineering journals and mill management handbooks. It served as a reminder that in complex mechanical systems, small effects can accumulate into large phenomena, and that standing still is not the same as being at rest. Even in silence, even in darkness, massive structures can be alive with invisible forces, waiting for the right conditions to make themselves known. The chalk marks on mill number 3's drive shaft became a legend among New England millwrights, a story of steel that remembered, buildings that breathed, and the patient unraveling of a mystery that should not have been possible.